We're going to talk about concavity and points of inflection. What that is, let me give you a little graph to kind of see what I mean by concavity and points of inflection. If that's my graph, all right, this right here is called a point of inflection. Now the reason for that is the concavity changes at that point. And here's what concavity is. Concavity is basically when you see a graph that is kind of frowning, that is called concave down. Okay, when it's kind of smiling like this, it's concave up. So this is concave up, this is concave down. All right, when something is concave down, the second derivative is negative. When it's concave up, the second derivative is positive. And this point right here is called a point of inflection because that's the point where the concavity changes. All right, so basically if you see a frown, it's sad, it's negative. Oh. If it's happy and smiling, it's positive, happy, smiling. So concavity, points of inflections, and we're going to find those and deal with those in this problem. In order to do that, the first thing you do is find the second derivative, because concavity changes at the second derivative. That's where you see your concavity. So the first thing we're going to do here is find the second derivative. So in this problem, it says find all points of inflections and discuss concavity of this graph. So for what we're going to deal with here, the first thing we're going to do is find the second derivative of this function to deal with concavity and points of inflections. So the first thing we're going to do to get a second derivative, we first have to find the first derivative. All right, so to get the first derivative, what do you get here? Well, the derivative of x to the fourth is 4x to the third, and the derivative of this is negative 36x. All right, halfway there? No, the second derivative. All right, so to get the second derivative, we take the derivative of the green part here. All right, so let's derive this now. If we derive the first derivative, we'll get the second derivative. All right, derive 4x to the third, I get 12x squared. When I derive negative 36x, I get negative 36. All right, first step was to find the second derivative. Did it. Okay. Find where the second derivative equals 0 or where the second derivative does not exist. So this always exists. There's no number I could plug in where this does not exist. So I don't have to worry about that piece, but you will have to on other problems. But what we're going to do is we're going to set the second derivative equal to 0. So set this equal to 0, and I'm going to solve it. Okay. So I got 12 x squared minus 36 equal to 0, and I'm going to solve that. In order to solve it, I'm going to add the 36 over, and I get 12x squared equals 36. Divide by 12. I got x squared equals 3. And then you get rid of a square, we square root. So I now have x equals plus or minus the square root of 3. All right, that is where the second derivative equals 0. All right, next, make a table with these values, those two values, as breakpoints. All right, so here we go. I'm going to make a table, a number line. All right, and what I'm going to do here is I'm going to make these values as breakpoints. All right, so I'm going to make one of the breakpoints the negative square root of 3, and the other breakpoint is the square root of 3. All right, so make a table. Those are my breakpoints. Okay, next. If the second derivative is less than 0, which is negative, then the function is concave down. If the second derivative is greater than 0, which is positive, then the function is concave up. So, well, on this interval, what I'm going to do is I'm going to plug a value on this interval, and on this interval. If I plug a value in here, and it's negative, it's concave down. If it's positive, it's concave up. Okay, because negative is concave down, sad. Concave up is happy, positive, negative. Helps for remember what we talked about up here. All right, So what I'm going to do is I'm actually going to plug a value in from each interval into the second derivative to see if it's positive or negative. So here we go. I'm going to take and plug in a value again to the second derivative, and I need a value on this side of negative square root of 3. Would be an easy number. Well, I'm going to put a negative 2, just some number on this interval. When I do that, into the second derivative, okay, when I do that, I put a negative 2 into here, you get 48 minus 36, which is 12, which is positive, which means this interval is concave up. It's happy. Alright, now I got to choose a value in this interval. Alright, into my second derivative, I think 0 would be a really good one. So let's do 0. When you plug in 0, 12 times 0 squared is 0. Nice. Minus 36. So that's negative 36, which is negative, which means it's concave down. Sad. Alright, and then the last interval, what's something in this interval? Well, if negative 2 is over here, let's do positive 2. That should be pretty easy. So 2 squared is 4. 4 times 12 is 48. Minus 36. That looks familiar. 12. Positive. Concave up. Okay. So we just found out that our concavity for each area, each space. The last one, if the concavity changes at any breakpoint, then it is a point of inflection if the coordinate actually exists. So there has to actually be a coordinate, and then we know it's a point of inflection. So the question asks again, find points of inflections and discuss concavity. So at these 2 points or breakpoints, did my concavity change? From here to here, well, yeah, I went from positive to negative. From here to here. From here to here, well, yeah, I went from negative to positive. So at these 2 points, the concavity changed. Now we got to make sure they actually exist. So we got to find the value at these 2 points. All right. So here we go. We want to find our points of inflections. But before we do that, the question asks for discuss concavity. So for this interval, what's this interval, this first interval? Well, for this interval right here, all right, let's call that interval from negative infinity to negative square root 3. That interval is concave up. All right. For this interval, which is from negative square root 3, okay, to positive square root 3, that one is concave down. And from this last interval is from the square root of 3 to positive infinity, that one we said is concave up. I could write the words, but this right here is actually part of my answer. Okay, again, it might be better to say concave up, concave down, concave up. It's probably better, but those are my intervals for them. So I answered this part of the question. Now I want to check to see if the actual points of inflections actually exist. We did say that the concavity changed. See, that's a point of inflection because concavity changed. Sometimes concavity won't change. So let's see if these values actually exist. Well, my points of inflections, I call points of inflections P of I. Points of inflection is kind of a long word, so I call them P of I. You don't have to call them that. And I want to find coordinates here. So I would have negative square root 3 comma something and the square root of 3 comma something. Now, what would the values be if I plugged them into the original function? Well, if I take the 4th power of this minus 18 and the 4th, and then this squared, well, the square root of 3 negative, taking the 4th power, the negative actually doesn't matter in this one because it kind of disappears when you take an even power. But wouldn't that be 9? So wouldn't that be 9, and wouldn't this be 3? So you get 9 minus 18 times 3. And what you end up with is negative 45. Okay. Now if I plug in this, well, aren't these both going to give the same answer? Because negative or positive with these even powers, they're going to end up with the same answer. So both of these would be negative 45. So those are my coordinates of my point of inflections. They actually exist, and they exist as well as they change concavity, like I said about that earlier. So the first step is always find the second derivative. Then you got to see if your second derivative equals 0 or your second derivative does not exist. Kind of like critical numbers of the second derivative. Critical numbers do the same exact thing, but you're doing a second derivative. So we checked where equal to 0, it never did not exist. We made a table, breakpoints. Then we checked a value in each table, each interval, to see if it's up or down, negative or positive. That gives me my concavities. And then I checked to see if my concavities changed, to see if it's a point of inflection. So at each break, it is a point of inflection, and we get the coordinates to make sure they exist. And those are the actual coordinates of the points of inflections. All right. So concavity is a really important thing. Points of inflections are really important, and they actually help you make graphs in the future. So good luck with this section.